Okay, we're on the home stretch here in the 2021 PAT. So we got up to question 22, which means we've got 3 left. We've got to start here by sketching the functions. Well, those two things here. We've got a quadratic and 2 over x. We've got to sketch them on the same graph. Now, they usually want us to put intersections. So let's look on, part B. Determine the coordinates of intersection of the 2 curves. Label their exact values. You're not required to get intersections with the axes. Right, so we're going the easier one to draw on these typically wonky axes. So the 2 over x one's going to be easier because that's just going to be this sort of thing going on. Making care to keep that as an asymptote there. So that's our 2 over x. So we need our intersection points. I mean, that quadratic is going to be shifted to the left and down. We got left because we got a plus there and down because we got a minus there. So we're going to have something, but I'll get the intersection points and then draw it on. I think that's going to make it easier just to pinpoint where everything is. So x squared, well, actually, let's multiply through by the, I've started now. I was going to save a bit of space by multiplying through by the x before I start. So we've got x cubed plus 2x squared minus 7x minus 2 is equal to 0. So one isn't going to work. They're bound to have an easy factor here. What about 2? 8 plus 8 minus 14 minus 2. Yeah, so 2x minus 2, which leaves us with x squared. We'll need a 1 at the end, which means we're going to need, a plus 4 in there. That's annoyingly not going to factorize. So we've got x is 2, or we're going to have x equals 2, or what is this going to be? X plus 2 squared. We've got to take off 4, add 1, so that'll be equal to 3. So we've got x is equal to minus 2 plus or minus root 3. Right, so we're going to have, they're there and there. Right, so let's draw this in, something like that. That's going to be at 2 for x, which means we've got 1 for y. And then we've got these points here, let's call them A and B. So A is going to be it's the lower x coordinate, so minus 2 minus root 3. B is going to be minus 2 plus root 3. And now we've got to work out, I'm just going to scroll down a bit, some annoying y coordinates. So we need 2 divided by that. So 2 divided by minus 2 plus root 3. So we'll be multiplying top and bottom by minus 2 minus root 3. So what would we get on the bottom? We're going to have 4 minus 3. So that's going to disappear. So we're going to get for, which one was it? Oh, actually, I've done B first, haven't I? So that's going to be minus 4 minus 2 root 3. And then we're going to have, what's the difference on that? We're just flipping the sign on the square root. So that would be minus 4 plus 2 root 3. Okay, so that's a bit messy, but there you go. That was fairly straightforward anyway. So so that's those ones. That's our 3. Is that all they wanted? Let's just double check as it's gone off the screen. So I've sketched them both, and we got the intersection points. Yes, so that's good. Evaluate the finite area enclosed between the 2 curves. Oh, sigh. Right, so that's going to be, so the ones with the really annoying x values. And a really annoying function as well. Oh, good grief. This is going to be really, really tedious. It really is going to be tedious. Anyway, so with this, let's set out the integral first of all. We're going to have these areas are going to be negative. So let's take the bigger magnitude area is going to be the quadratic. But we'll make that negative to make it positive, if that makes sense. So we're still going from minus 2 minus root 3 to minus 2 plus root 3. And that's going to be our x squared plus 2x minus 7 dx. And then we're going to have to take off the negative, so add on the integral between the same limits of 2 over x dx. I won't bother writing the limits in. Right, this is going to be a lot of messing around, so it's probably worth doing this in chunks. Otherwise, yeah, because we've got a lot of terms there. Right, let's make a bit more space. Well, I'll do the integral and then see if there's some better way of arranging all of these things. So we've got x cubed over 3 plus x squared minus 7x. Oh, so plus x squared, I wrote out 2x, right? So that's that between minus 2 plus root 3 minus 2 minus root 3. So that's that bit. And then we've got, that's just a 2 log x between the same limits again. Right, so yeah, it really is going to be messy. I don't think there's anything in the way of a shortcut we can do on this. I don't think. I think it's just a case of writing it out bit by bit. I mean, we might have things that are cancelling, so I'm going to do them one at a time. So for the first one, so our x cubed over 3 1, we're going to have a third. Let's take that outside. I'll put the minus sign back in later on. So, but we'll have a third of minus 2 plus root 3 cubed minus 2 minus root 3 cubed, which means we're going to get the third of, what is all this? It's going to be minus 8 plus 3 root 3, then minus, how many, that's going to be 18, isn't it? Because we're going to have 3 times 3 times 2, and then for 3 times 4 times root 3, so plus 12 root 3. Then we're going to have to take off, we're going to have minus 8 again, minus 3 root 3, minus 18 will stay the same, and that one will flip sign. So some of them have flipped signs, some of them haven't. So what we got, the 8s are going to cancel, because we've got the minus 8s. The 18s are going to cancel, and we're going to be left with 6 root 3 plus 24 root 3. So 30 root 3 divided by 3 is 10 root 3. Okay, the x squared one. So we're now going to get, well, minus 2 plus root 3 squared minus 2 minus root 3 squared. I suppose I could do difference of 2 squares on this. So we'd have minus 2 plus root 3 minus 2 minus root 3 multiplied by minus 2 plus root 3 plus 2 plus root 3, if I can say it correctly. So they're going away, they're going away. So we got minus 4 times 2 root 3. So that's minus 8 root 3. Then what we got left, the minus 7x one. That might have dropped off the screen, but minus, let's move it in a little bit. Minus 7x term is going to be, so what we got there, we're going to have 14 minus 7 root 3 minus 14 minus 7 root 3, which is minus 14 root 3. So all in all for that, we've got 10 minus 22 root 3, so that's minus 12 root 3, and we got the minus sign. So we add all of that up and we got 12 root 3. Now we got to do the log one. So I'll squeeze the log one here. I mean, I'd like to go further down the page, but this is going to be quite short. We're going to have 2 log of minus 2 plus root 3 divided by minus 2 minus root 3. So when we rationalize the denominator, so we're going to be, well, squaring the thing on the top, and we already know it gives 1 on the bottom. So that is going to be 2 log of minus 2 plus root 3 squared. Okay, and we just got to add those together. So that should be taking something off. Yeah, that's right, because yeah, minus 2 plus root 3 is going to be between 0 and minus 1. We square it between 0 and 1, do a natural log of it, which makes it negative. So that's okay to add on. So our, was it minus 2 plus root 3? So we've got 2 log minus 2 plus root 3 all squared. and we need to add that to 12 root 3, and that is our area. What an epically boring question. There you go. I think you should get more marks just for refusing to do it and putting a protest on your paper. But yeah, there you go. At least we got it out of the way. I mean, this is the same paper where they gave us that other stupid question earlier on where we had all the boring stuff. And no wonder they've given a lot of working out space. Anyway, at least that's done. Right, the potential energy for a system of two atoms separated by distance x is U of x shown below. Sketch the negative of du dx. What does this new curve represent physically, and what does the point x0 represent? Right, okay, so right, this is one of these ones that once you've done a physics degree, you know what this is going to look like, which gives you something of an edge on this. Obviously, I'm assuming you don't, because that's why you're doing this, you're prepping for this paper, because you want to do a physics degree, you haven't done it yet. Chances are you're not going to just look at this and know what it is. So let's, I mean, I don't know whether to draw it up first of all. Okay, we're going for something which is looking a bit like this. It looks very similar, the answer that you get, but maybe with a little less curve on it. Very hard to draw it exact on here. It's going to be looking a bit like that, slightly less bowing on it. But how are we going to end up with this? But I just want to let you know I've already got this in mind when I'm sketching it. So I'm going to try and explain how you do it anyway. Now, we need to be looking here at the gradients then. So let's think about what's happening with the gradients as we go through here. So we've got very negative, and it's still very negative, and then it gets still negative here. Then we go to 0. Then we've got, yeah, I suppose before we get to 0, we've got a little bit negative. And then here we've got a little bit positive. Then we're getting more positive. And then we're going back again to little bit positive. So yeah, this is what we wanted to go through. Now, when we've then got this very negative gradient, we're going to again multiply that by the minus sign and get something which is very, very positive. So when we're drawing this out, I'll give myself a bit more space on our axes. So we know we've got to start up here because we've got something very negative multiplied by -1. Then we're going down, down, down. Let's see what happens when we get to this 0 point then. So when we got 0 gradient, that must be when we're crossing the x-axis here. And that is then, well, that's our x0. And we know that between here and there, the gradient is decreasing. So between our starting point up here, where we've got this huge positive number, the gradient is decreasing. So our value is decreasing until we hit that point. I'm going to come back to this section a little bit later on. Then we've become a little bit positive on the gradient here, and the gradient is increasing up to say there. It's getting more positive. So we're getting more negative. Then we hit this point here where we've hit some kind of maximum positive gradient, which is going to be then our maximum negative value. And then the gradient is going to go back, it's going to be less and less and less positive. So it's getting less and less and less negative when we multiply it by -1. But we never make it back to 0 because we've got an asymptote here, so we'll have the same thing on the other side. Now, one of the things that can throw people is drawing this section here, this part, like these positive value that we've got here, because it looks like, okay, we've got very negative, we're still very negative here. You know, why isn't this staying at some huge positive value once we've multiplied by -1? As in, why aren't we getting something that's looking more like this and then dropping off? You know, why is it coming straight down? And this is quite a difficult one to visualize. But when you've got something which is approaching an asymptote, as you've got here, when you've got very, very steep gradient, let's try give myself a bit more space. So you've got a crazily steep line. I mean, I've even flattened that out a little bit. But if you're going through the same bit of the same x step, let's say you've got that amount there, then even if you've got that amount of change in y, for a certain change in x. You only need a tiny change in the apparent gradient. By the time we've got down here for the same x step, then we've got, say, that much difference. So you're getting a big drop in the gradient, even though it might not look like it. And that's what you get when you get these really steep lines. So this line is even steeper than the one that I've drawn there. So, you know, a change in y that you're going to get for the same x step from here to, say, here is going to be enormous. So that's why you are still getting this decrease here for what becomes this positive value. Yeah, because it's just the crazy thing of looking at extreme gradients. So, but the reason that you'll become familiar with this pretty quickly when you start doing your physics degree is we know that this ends up being force. I've actually spoken about this in my classical mechanics videos, that you can think of force as being a potential energy gradient. So that's what we've got here. We've got a potential energy gradient. You know, U is the potential energy. So that gradient, that change in potential energy through space, is what force is. So you can actually, if you haven't done this before, you can go back and look at all of your classical mechanics again and start thinking about all of these forces. You know, go back to thinking about gravitation in classical mechanics, and instead of just doing all your, you know, your G's or your GMM over R squareds, think, well, let's start looking at all of this in terms of potential energy gradients. And you'll see, you know, you've immediately got a link here between the potential energy and the force. You know, we've got the 1 over R and the 1 over R squared relationships going on there. So yeah, force is a potential energy gradient. So what have I got here? So yeah, what we're saying here is that represents force, the new curve, and the point x0. So if we got 0 force, because this is now where we're cutting the axis here, this is our new force versus distance graph. So here we're saying we've got no potential energy gradient, we've got no force, it's an equilibrium point. So I would say this is a pretty tough question if you've never seen it before. If you have seen it before, probably unlikely, but if you have, then it is quite straightforward. But if you haven't, that is a very difficult 4 marks to get hold of. So there you go. Anyway, that's question 23. Pushing on, we come to question 24. This might be the last one. I think it is the last one. So fingers crossed this isn't too long-winded. Right, we've got f of x is that thing, g of x is this, and they look pretty similar. Maybe this is going to be to do with transformation of graphs or something. Then sketch f of x minus ct plus g of x plus ct for 3 different t's. Right, so they're moving them through space. So this isn't going to be transformations, or, well, it's got transformations in it. Obviously, we're transforming the graphs. But this is going to be, what's the word, interference. It's going to be superposition of waves. Because we've got, now they're making these functions of x and t. You know, t is changing. So they're setting these waves in motion. They're moving f of x off to the right with time because we've got a minus sign here. They're moving g of x off to the left with time because we've got a plus. And then these things are going to overlap and we're just adding them up. So they've given us 3 different times, and we just need to say, well, what everything's going to look like. So I'm going to write these times here because we've got real issues with space. Actually, that's a half a over c, that's 3/4 a over c, and then we've got just a over c. So what are we getting on these? So we want to have, this will then become, we're going to have f of x minus ct. So that will be f of x minus a over 2. And then we're going to have f of x minus 3/4 of a, and then f of x minus a. And then we're going to have all of these for the g's, but with pluses on. So yeah, we'll have g of x plus half of a, g of x plus 3/4 of a, and g of x plus a. Right, so we're going to want to well, if we think about what they are separately first and then start overlapping them all. So how are we going to break these up? Everything's moving in, I think, quarters of A, which is annoying considering we're going up to 2A and minus 2A here. Right, let's try drawing these in. Well, this last one's easiest to draw. If we're moving it A to the right, well, that's just going to be looking like this, isn't it? That's fine. And then this is moving A to the left. So it's going to look like that, which means they're exact opposites of each other. So we've got that one sussed already. So this is going to be, so if we do f of x minus a plus g of x plus a, then we're just going to get a flat line because they're just going to completely cancel out with destructive interference. So it's harder to draw it. So you might want to write on it that is destructive interference. So that one was easy. Let's change color on this then. So we have a bit of red. So a over 2 is going to be an easier one to draw. The 3/4 one will just be in the middle, so maybe that'll be easy when we get to it. So the a over 2 one is going to be halfway between. These are all meant to be straight lines. It's not as like drawing on here. So we've got the peak here then is going to be at minus a over 2. That's going to be at a over 2. Oh, and that's going to be at a over 2. So we've got the peak aligning with the bottom. So when we're on one side of it, where can I draw this? Let's do a small picture over here. I think that's still just about on the screen. So from minus a over 2 down there, and then from a over 2 to there, that's all unchanged. So that's a over 2. This will be 3a over 2. That will be minus 3a over 2. That's going to be at minus a over 2. Now we just need to work out what's going on between those peaks. So the top wave is dropping off at the standard gradient. The bottom wave is also dropping off with the standard gradient. So we're going to be dropping off with double the gradient. And just to check, so yeah, this is going to be, that's the opposite of that. That when we've got x is 0, we got half a and minus half a. So yeah, it's going to go through the middle, and that fits in with it being a double gradient straight line through there. Okay, so that's good. Now we've got a problem of doing the last one. So let's go to some green. So because we've got some really annoying values. So if we move 3/4 of the way along, I'm going to have to draw this out again. So we're going to have the peak at minus a over 4 and a over 4. All right, let's move down. I think we've got a handle on what's going on here. So we're going to have, oh dear, that's gone off, isn't it? So now our positive one is looking like that. Our negative one will be looking like that. We've got a lot more overlap. That's at minus a over 4. This peak is at a over 4. So we've moved 3/4 along. So the bottom there is going to be at minus 5a over 4. This is going to be at 5a over 4. So when we're putting these together, what are we going to end up getting? Well, we know we're going through 0 here. We know we're going through minus 5a over 4. We know we're going through 5a over 4. We know that so what have we not got overlapping? Let's think about this as to where we are. So this is coming in the middle, is it? Well, let's think of where that's minus over 4. So yeah, we got a in between. I'm trying to work out what this coordinate is here. That's going to be halfway between these two, isn't it? Yeah, that's going to be minus 3a over 4. Yes. Well, yeah, it's got to be. So that is meaning we're halfway up there. That's going to be at a over 2. So we've got a bit going to there at minus 3a over 4, where we're at a over 2. We've always got exactly the same thing, but opposite on the other side. So that is going to be going to 3a over 4 and at minus a over 2. We know we're going through the middle again. So what's happening? So as we're going from, say, here to here, the top one's going up and the bottom one's going down, but the rate is going up is the same as the rate is going down, so it's going to be flat. So that'll be flat until we get to minus a over 4. And we'll have the same on this side. It will be flat until we get to a over 4. You know, an A, not a 9. It's an A. And then we've got both of them coming down. So it's going to be the old double gradient thing like we had before. So it'll end up looking like that. Yeah. Well, that wasn't anywhere near as bad as I thought it was going to be. The difficulty is they've done it all steps in quarters, which I think has made it more tricky to work out what all of the x values are. Because, yeah, we're doing sort of eighths of the whole span of it. Let's just double check I've got that right on here. The total extent of that is 10a over 4. So that's 2.5. When originally it was 4. So we've moved 1.5, which fits with being 2 lots of 3/4. Yeah, okay, that was a nice question to finish off with. I didn't. That was interesting. And 23 was a nice question. Question 22 was just ridiculous. So no imagination in it whatsoever. It's just boring. But still, that's finished off PAT 2021. So 2 more papers to go.